Learning robust task priorities and gains for control of redundant robots. Redundant robots like humanoids or mobile manipulators can simultaneously perform several tasks. The usual way to control these robots is to formulate the problem as a multitask quadratic program, where the tasks are organized according to defined priorities and the goal is to minimize the task's errors while satisfying a set of constraints, such as joint limits, collisions, etc. Finding the task priorities together with the task gains is often a time-consuming trial-and-error tuning procedure that requires human expertise and many tests on the robot. Here we aim at the automated offline optimization of such parameters for generic multitask controllers. For a given task, the QP control consists in solving the following optimization problem at each control time step, where you use the control input vector, for example joint velocities for inverse kinematics or joint torques for inverse dynamics, A the equivalent Jacobian matrix of the task, epsilon regularization factor used to handle singularities, the constraints concern those quantities like the control input, limits, dynamics, collision avoidance, and contact-related constraints, and B is the reference for the task. If we have a multitude of tasks, then we can consider them at a different level of priority. And we can either consider strict priorities, that is hierarchical structure, also known as stack of tasks, or we can consider a weighted combination of the tasks, where the weights are the soft priorities. In this work, we considered a generic control structure with both soft and strict priorities. So the parameters that we want to optimize are the soft weights, the level activators that encode the hierarchical structure of the controller, and the convergence gains. In inverse kinematics, the reference value of the task indeed is given by the feed-forward velocity term plus the convergence gain multiplied by the Cartesian pose error. In the literature, many approaches have been proposed to learn the task priorities. When both the soft and the strict priorities are learned, this is done for few tasks and or in simulation. Also, optimal control has been combined with movement primitives to obtain solutions that work on the real robot, but relying strongly on the accuracy of the simulated model. Differently from previous work, here we propose to learn both the structure of the controller, the position of each task in the hierarchy, and all its parameters, the task weights and convergence gains. We optimize for a large number of tasks and introduce a parameterization of the strict priorities that allows us to optimize them as simply as the soft weights. And we look for solutions that are both high-performing and robust by relying on multi-objective optimization. Multi-objective optimization relies on the Pareto dominance concept. A solution x1 dominates x2 if and only if x1 is better than x2 for all the objectives. If x2 is better for at least one objective, then x1 and x2 are equally interesting as they represent different trade-offs. Using this definition, optimizing means finding the set of non-dominated solutions of the search space, that is, solutions that cannot be improved with respect to one objective without decreasing the score with respect to the other. This set is called the Pareto front. Here's a flowchart of the learning procedure. First, the multi-objective optimization process based on rollouts performed on a simulated robot model computes offline a set of Pareto-optimal solutions. And each solution is a control configuration that trades off different performance criteria, optimized on a training sequence. Then, the user selects candidate solutions from the Pareto front and validates them on the real robot using test motion sequences. And here the purpose is to find transferable solutions that are high-performing and well-balanced. So the first block of our method is the motion generator. That's a module generating a sequence of robot movements defined by reference trajectories. Any motion planning algorithm could be used, but in this work, without losing generality, we used our motion retargeting framework. Then, the algorithm that we opted for is NSGA2, one of the most efficient stochastic multi-objective optimization methods. The objective functions are the accumulated tracking error and a robustness score. That's a measure of the Z and P position inside the subpolygon. Basically, we want to minimize the distance of the Z and P from the center of the subpolygon. And we want to minimize these two cost functions. We additionally consider a third objective function, consisting of a fall avoidance score. This is not strictly necessary since this information is already encoded by the other two cost functions, but we included it to help the convergence of the algorithm. So we can never get simultaneously a bad score for the fall avoidance and a good score for the tracking error and the robustness score. So all the dominant solutions composing the Pareto front have fall avoidance equal to 0, so the robot does not fall. And we can then analyze the 2D Pareto front related to the cost functions tracking error and robustness score. By using a motion generator that considers 4 tasks in the joint space and 8 tasks in the Cartesian space, we have 26 control parameters to optimize. We obtain this Pareto front by using this learning sequence. We report here the most high-performing solution obtained in simulation. To find an optimized working solution on the real robot, we start from the most high-performing solution. That's the one with lowest tracking error and highest robustness score. And we try if the solution works on the real robot. If not, we move progressively to solutions that are less high-performing and more robust until we get to a solution that achieves balance on the real robot. The solution is transferable onto the real robot, and we report here the associated optimized parameters. We compare this control configuration with a hand-tuned baseline controller on different test sequences. On the first sequence, we see that the learned configuration outperforms the baseline. In a second sequence, we retuned the baseline controller in order to avoid that the robot falls in simulation. However, the robot falls in reality. In a third sequence, we even used for the baseline controller the same task priorities of the optimized controller to show that even the convergence gains have to be optimized. Indeed, the real robot falls with the hand-tuned controller. To show how a controller optimized through our approach can be used for generic motions, not previously encountered in the learning sequence, though from the same category, that's double support motions, we repeated the same procedure by using a motion generator that we can use to teleoperate the robot. We teleoperated the iCub to perform several actions. For example, here the robot is opening the door. The robot is fully teleoperated, which means we target the human motion and the robot controller is capable of safely executing the different motions without falling. Then the robot can close the door, and with the same control configuration can also pick up a box and hand it over a human operator. And we can perform several other movements. The different movements could be executed in a very optimal way by different controllers, each optimized for the specific movement. Instead, with our method, we have one single controller that is empirically robust enough to execute them all. Our approach is not robot-specific to show that it can be applied to other robots with a different kinematics. We optimize the controller for the common robot, and the solution is shown in simulation for a short squat motion. So we propose a framework to automatically learn both the structure and the parameters of a generic whole-body controller. We use multi-objective optimization to look for solutions on the Pareto front, representing optimal trade-offs of performance, tracking the reference trajectories, and robustness, limiting the tipping moment of the robot. This allowed us to efficiently find a set of Pareto-optimal trade-off solutions in simulation. The user can conveniently choose from the Pareto front a pre-optimized solution to test on the real robot, and this reduces considerably the number of test trials on the real robot and improves the parameters tuning. To give the audience an example, to find a suitable control configuration for humanoid teleoperation, it only took us 3 test trials on the real robot. So in this work, we limited our approach to double support motions with a simple QP controller structure. More complex and dynamic motion will be addressed in future work. Thanks for watching.